Hello everybody, how's it going? This is the third episode of the Mathematical Physics series. So what I would like to get through today are some techniques in reduction, finding hidden symmetries in systems, and the inverse reconstruction of even if we know nothing about a force. Motion itself, here we'll kind of work through an example of the period of an orbit as a function of the energy. We could be able to just reconstruct kind of a potential. So let's look at first the reduction of the two-body problem into a single body. And this might seem like a very simple exercise, but it's very deep and it's an important technique in physics. So let's work with two particles, because essentially they become the same particle. So we'll say M1 and M2 with positions Q1 and Q2 in R3, and the canonical momenta are P1 and P2, and the phase space will be the cotangent bundle with R6. Now, it's going to have a standard kind of symplectic form. Let's write out that omega better. With our dq for the first particle, wedge dp for the first particle, plus the other particle wedged here. All right. That define this volume in phase space. The Hamiltonian for a central interaction is really going to depend only on the distance. So because it is a central interaction, the absolute distance between this is going to determine the Hamiltonian. Which is a function of the positions and the momenta. And in fact, let's write it out fully. So it's going to be the momentum squared for the first particle, basically the kinetic energy terms here, the momentum squared for the second particle, plus the potential as a function of this central interaction. Now, translating both of the particles by the same vector A. So if we translate them, let's say we send Q1 to Q1 plus A and Q2 to Q2 plus A. This leaves a separation vector Q1 minus Q2 unchanged, right? And also the momenta are unchanged. So the Lie group is acting on phase space by phi A, Q1, Q2, P1, P2 to be Q1 plus A, Q2 plus A, P1, P2. And so the infinitesimal generator, or the vector field for the translation vector, basically the element of the Lie algebra for R3, becomes C V dot Q1 plus V dotted with Q2. And if we contract this vector field, if we contract this vector field with the cotangent bundle space valued on the cotangent bundle, we'd have v dp1 plus dp2 to be d v dotted p1 plus p2, right? And this becomes our momentum map. And the momentum map for the translation symmetry here just becomes the total momentum. All right? And so what we can do is, sorry, let me get a drink real quick. And chew some ice. So the translation action is free and proper. Now, because we can do this, or because it's free and proper, and we have this, we can fix a value of the momentum map. We can fix some value of this, and then a quotient by the residual isotropy, which is still all of R3. So if we choose the center of mass frame, so let's say choose that J is equal to 0, P1 should be equal to negative P2, or vice versa. The translations are going to still be present, that we're going to move the whole pair of particles together, but we're going to take the quotient of the action by A. We're going to quotient out the symmetry that we had here, this symmetry, and the resulting reduced phase space is going to be diffeomorphic to this cotangent bundle of the relative coordinate. So to make this explicit, we can introduce a linear change of variable. So let's say we call R, capital R, M1 Q1 plus M2 Q2 over M1 plus M2. And then the relative coordinate will be the difference between Q1 minus Q2. The total mass will just be M1 plus M2. And the reduced mass coordinate will be M1, M2, M1 plus M2. Okay? So the conjugate momenta then, they're going to, let's have a capital P represent the total momentum. Sorry, should be 1, P2. So total. And let's have little p represent M2, P2 minus M1. Sorry, this should be a P1. It's relative. This will be the relative momenta, so that we can have the symplectic form omega be written out as dri and dpi plus dri dpi. And what this will do is it allows us to have the Hamiltonian itself separate with this new coordinate system. And what we now have is a reduced phase space. And remember, the total momentum, we set P to be equivalent to 0, and R is quotiented out. Right? And so we thus just have a one particle system. So it's called the relative Hamiltonian. We just have a one particle system. So the 6-dimensional phase space basically with canonical coordinates r and p. So we basically had this original 12-dimensional problem, right? With the momentums and the positions, right? Yep, with the momentums and positions in R3, we had four. We had four of them valued in R3, and the phase space itself was the cotangent bundle in R6, but we proved that it became diffeomorphic with the symmetry, or with the Lie algebra. And hence, we're left with a 6-dimensional problem. So this 12-dimensional problem is now way easier, okay? Because we only have to deal with these two canonical coordinates. So it's a fixed 6-dimensional phase space. Very, very nice. Now, and of course, we've compressed this by discarding the center of mass degrees of freedom that actually don't affect the inertial motion to begin with, right? Because they're moving together as a body. Now, what we can do now is take the inverse distance potential. So let's say VR is equivalent to kappa r, with r being the magnitude of that separation vector, and with kappa being greater than 0 for an attractive force. Okay, so the reduced Hamiltonian is the kinetic energy plus the potential energy, which is attractive. And there's an obvious rotational symmetry because that we assume. So if we have an angular momentum vector, if we take the cross product of the the conserved quantity for the angular momentum vector is the cross product of the r and p canonical coordinates. And the components of this conserved angular momentum vector, as we know, satisfy the SO3 Poisson bracket algebra, which takes the components of the angular momentum vector as the Levi-Civita tensor with the kth component. All right, so that's the Poisson bracket algebra. This should be review. But the Newton's equation. So if we take, this is Newton's equation, if we take the center of mass coordinate and the acceleration of that coordinate to be 1 times the position vector times the magnitude of it cubed, this can be manipulated to reveal another constant of motion. So if we were to compute the derivative, let's compute the derivative of the time derivative of the momentum crossed with the angular momentum. So if we cross the momentum with the angular momentum, that should be equivalent to the momentum dot with the change in the momentum with the angular momentum. But assuming Newton's formula, we know that that should be equivalent to KR3 R cross P as a vector identity. And then that should give us mu K, or mu kappa, d by dt, where this is our vector. So that's kind of the trick that we have. And so there's a particular vector that becomes conserved, that we can rewrite as conserved, following from this logic, which is that, let's move it over here. We can write this vector as 1 over mu of P cross M minus kappa of R over the magnitude of R. So the separation vector. This itself is conserved, and this is called the Runge-Lenz vector. And it satisfies this orthogonality condition that if we want to take this dot product with M, that should be equivalent to 0. And the magnitude of this vector, so if we take the magnitude of this vector, that will evaluate to this quantity, which implies kappa squared plus 2 times the Hamiltonian. Basically, it's related to the energy. All right? So this vector itself can be related to the energy with these conserved quantities and this attractiveness of that force that's keeping the orbit together. Okay? Or keeping the attraction force together. All right? Not assuming an orbit yet. Now that we're aware of this particular type of hidden symmetry that comes from basically taking Newton's equation and also the time derivative of the momentum cross the angular momentum in this nice center of mass frame of reference, we can use the canonical Poisson brackets. So let's take the ith component of our radius vector with the jth component of our momentum and kind of do a Dirac delta. Now, by taking these canonical Poisson brackets, the angular momentum brackets are already known. So the remaining non-zero brackets that we can play around with are mi, aj, Levi-Civita, ak for the cyclical permutations, and then also ai, aj equals to 1/2 mu h cyclical permutation Levi-Civita connection on m sub k. And for a bound orbit, so for the energy, h being basically h being less than 0, we can rescale the Runge-Lenz vector to absorb the energy dependence. So rescale to absorb energy dependence. A prime would be A for this vector minus 2 square root of minus 2 mu h And by doing that, the this rescaled vector will then give us brackets that look like MIAH there. In terms of Levi Civita, JK, oop, and then AJ equals Levi Civita M sub K. All right. So this together with the original SO3 Poisson bracket algebra, so this guy together with this, the 6 quantities. So we kind of have that these 6 quantities here are going to here, let's make a new page. So let's write them out. We have MI, the rescaled version of our Runge lens vector. Okay. And then sorry, I'm crapping on this. A prime K. This gives us the kth component of M. And then MI and J. Okay. So the 6 quantities from M and A prime, they satisfy the Lie algebra SO4. So to see, if you really want to see the structure clearly, what we can do is define 2 independent, let's say SO3 generators. And let's make sure that we're kind of cursive this because they're Lie algebra generators. So we'll have some we'll define the raising operator and then the lowering operator here. Okay. Then what happens is we can take the we can construct these. They're basically these like Casimir type of operators for SO3 IJ. But what's interesting is Levi Civita. So we have this, and then we'll have the commutation, or sorry, the Poisson brackets for the lowering operator here. And then we're going to have the extra one that ensures the Poisson bracket here is 0. The algebra SO4 will be isomorphic to the direct sum of the Lie algebras, of the SO3 Lie algebras. So geometrically, we have these 2 Casimir invariants that we're building. J minus and J plus. And they're related to the physical quantities themselves by just saying, well, here's the squares of these two operators, or the squares of these two invariants should be equivalent to each other, which would give us 1/4 that's right, it would give us 1/4 of m squared plus a prime squared. And then if we substitute in the definition, for the Runge-Lenz vector, where we square that, because we scaled it, remember? So we scaled it out. Minus 2hm. And it was defined here with the product of this thing here. What will happen is that we will quickly see this negative sign will give us 4h. These cancel out. We'll be left with a mu squared. Is this right? Yeah. Yeah, it's correct, because then it should all cancel out and give us a constant of kappa squared 8 mu h. And so for, okay, so geometrically, right, here's the invariant, right? This the two Casimir invariants are going to be equivalent to this quantity. So for some fixed bound energy, the motion is going to live on this co-adjoint orbit of SO4. And it's basically topologically S3 cross S3, the three spheres, we're quotienting it out by some discrete group. Essentially a three sphere. And then after we appropriately regularize it, the Kepler problem here was going to map to a free particle on the three sphere. So it maps to a free particle on S3. And the hidden SO4 symmetry right here explains why all bound orbits really are closed ellipses, and why profoundly the Runge-Lenz vector points exactly to the perihelion for all bound orbits. So in short, what you want to think is like a normal ordinary elliptical orbit in. So the key takeaway is any ordinary elliptical orbit in R3 is the projection of a simple geodesic motion on the three sphere. And that extra conserved vector that we talked about, A, is just this remnant of a higher dimensional symmetry that becomes manifest after you remove the redundancy of the full two-body description. All right? So that's a very elegant, nice way to put this. But now, taking some time to appreciate this, what we can do is move a step further. And suppose we know nothing about the force law. Okay? We know nothing about the force law except that the motion is bounded and potential is symmetric. That's all we know. All right, so we're going even further. Let me take another drink. So that's interesting, right? So the problem is, can we deduce the potential purely from the oscillation period as a function of the energy? And the answer is yes. It's called the abel integral transform. The abel integral transform. So let's first let's consider a particle of mass m. So particle mass m moving in one dimension with a potential u of x satisfying u of minus x is equivalent to u of x. All right? And that u of 0 is equivalent to 0. And that u of x is strictly increasing for x is greater than 0. The energy conservation is going to give us that energy is 1/2 mx dot squared plus ux, which implies that x, we can just solve for x dot here. Should be 1/2m u of x. Okay? Now, the time to go from the equilibrium point to the turning point xe, where u, the potential function of u of x as a function of e, is equivalent to e. The time itself will be t of e over 4 from 0 to x as a function of e dx over the square root of 2m e minus u of x here. All right? And the full period then will look something like 2 to the 2 over m of e over the square root of e minus u of x. Okay. Now, what we can do is change the variable to the potential. So, because we have that u of x is monotonic, or strictly increasing and monotonic for x is greater than 0, what we can do is actually invert the relation to obtain x as a function of u. So x as a function of u, with x of 0 being equivalent to 0, the derivative of x is just going to be dx over du. That's got to be greater than 0 as well. So if we change the integration variable from x to u is equivalent to u of x, we can have that dx is x of u du, and u as a function of this still remains satisfied. And what that does is this yields the Abel equation. 2m is equivalent to 0. Integrating from 0 to the energy of x prime u e minus u du. And then the Abel transform. So what the Abel transform is it's essentially a technique. Let's go over here. So let's go into using the abel transform. So the abel transform just says, let's see. It says if we have g of u and we want to get it to f of t, to be integrated from 0 to t, g of s over t minus s square root ds. The formal inverse of this is going to be 1 over pi times ds from 0 to s of f of t over s minus t, square root of s minus t dt. So necessarily that's an inverse. Okay, so if we apply this to this integral over here, right? If we apply this formula to the integral, what happens is we'll have that the function of e will be t of e over what? 2 square root 2m, and g of u will be x of u, so that we obtain that the derivative of x of u would be 1 over pi times d by du, integrating from 0 to the potential of te to square root 2m u minus e dE. And if we integrate from 0 to u, we can recover x of u. So x of u itself will just be the integral from 0 to u of x prime of u du. And we're getting a little crowded here, but the value of this integral will be 1 over pi, the integral from 0 to u du t e to square root 2m square root of u e dE, integrated with respect to du. And then if you use the property that the integral of the derivative of a function of the upper limit is just the function itself, because, fundamental theorem of calculus, it's high school, you should be able to show that with an appropriate boundary term, of course, it's going to vanish because the upper integral goes to 0. You now will be left with this abel inversion formula, which says that x of u is 1 over 2 pi square root of 2m integral from 0 to u t of e u minus e dE. And you'll find that the period here, t of e, this period is known for all energies from 0 up to u. And the function x of u, the inverse function u of x, is uniquely determined. All right? So this function here, the inverse function as well, both of these are uniquely determined. So, for example, let's apply this to the harmonic oscillator, just for argument's sake. So let's say we have u of x is equivalent to 1/2 kx squared. All right. the period is energy independent. So the period of this potential would be 2 pi m over k. Now, if you insert this constant period into our formula, which you're getting from u here, for 2 pi square root of m over k, square root of u minus e dE. Well, what that gives us is 1 over square root 2k dE over square root of u minus e, which then would be equivalent to u. Okay. Therefore, u is equal to k over 2x squared, which is the harmonic potential. All right. So that does work exactly correctly. And so let's take a look back at what we've covered so far. So we started with the two particles, right? The translation symmetry that kind of removed the 3 degrees of freedom, so center of mass position and 3 conjugate momenta, so the total momentum. And then we collapsed this 12-dimensional two-body phase space into a 6-dimensional effective one-body problem. And then we also showed that when force is exactly inverse distance, the reduced system exhibits not only just the obvious SO3 rotations, but also an extra conserved range lunge vector that, together with angular momentum, they generate a larger symmetry, SO4. This explains the closed elliptical orbits and points really to this geometric interpretation on the 3 sphere as really just ordinary elliptical orbits in R3 is just the projection of simple geodesic motion on the 3 sphere. And the idea of inverse reconstruction, so that we can strip away even the knowledge of the force law and just the mere observation of the period as a function of the energy, enough to recover the shape of the potential. So this is the classic Abel integral equation that can be inverted analytically nicely. So, translational motion, coordinate choices, and then even the explicit form of the potential. With mathematical physics, we are trying to recognize the degrees of freedom that actually truly matter, and which conserved quantities they carry, and how the observed motion that we have encodes the very laws that produce it. Right? Thank you guys for going with me on this one. This was a pleasure to do. And let's see, what do I have planned for next time? Next time, we will be talking about we'll see what we'll be talking about. All right. See you guys later.